Okay, so welcome to the third session of this course. And I decided I will follow my script, and for the examination, of course, this will be the most relevant part. But I decided to give some recall of the linear algebra background that we will use. And because linear algebra is often confused with the theory of vectors and matrices, so vector analysis, the discussion about whether the dual space of Rn is viewed as column vectors is Rn viewed as row vectors. It appears a little bit naive or harmless because a physical vector doesn't have a row or column shape. Now, the more abstract viewpoint is compared to the course is that we are having a situation where we are facing abstract vectors, and I will show you how to use the space of cubic polynomials, which we can also use very nicely in GeoGebra as an abstract vector space. And if you look at the cubic polynomial, if you plot it, you normally don't think about the coefficients behind it. On the other hand, we know if you do algebraic computations, you are computing with coefficients. So I think it's a nice example of a vector space where you can work with coordinate systems, choosing the coefficients as a coordinate system, of course, or with the functions as functions, which you can move around, shift, and so on. So let us recall some basic facts from linear algebra. We all know that the usual way of looking at a matrix and standard format is m by n. M is the height and the width of the matrix, is to say, well, it moves vectors x from Rn into vectors y in Rm. I will talk about the real vector situation, but you can later on, especially when you use the Fourier transform, we will work with complex valued vectors. So we will not make a distinction later on. But there's another much less popular viewpoint, which is of course equivalent, and that's the idea of MATLAB is providing matrix multiplication, which means it's providing a linear combination procedure. So if you're given in linear algebra course 5 vectors in R7 and you would like to do a linear combination with some coefficients, you need the right number of coefficients and you're summing up, and what you're doing is you put these vectors into a matrix. They all have the height of their columns, of course, and the number of vectors that you can linear combine is, of course, the n is the width of the matrix. So with the standard notation of using A1, A2 to AN as the denomination of the columns of a matrix A of standard format, you can say A times X is a kind of a linear combination of those column vectors. So clearly the target space, so the range of a linear mapping, is nothing else but the column space, the set of all these linear combinations. And you can say a matrix is providing a surjective mapping if and only if the columns are a generating system, or they are the linear mapping is injective if only each vector which is represented can be represented in one way, so that the injectivity corresponds to linear independence and so on. So a lot of standard formulations can be brought back to standard properties of mappings. Now, if you think a little bit, and I don't do all the details here, of course, this relationship of linear combination machine is equivalent to say if you apply a matrix to a unit vector, then you get the corresponding column. So apply a matrix to, let's say, the 5 by 5 matrix on the third unit vector, it will pick out the third column. So it's clear if it's like this, then by doing summation and multiplication of unit vectors, you get every vector. So every x is a sum of xk times unit vector ek. And therefore, if you use the second formula to get the first formula, then you're in a good business. And if you take the first formula and specialize it, they say, okay, if your list, you order a linear combination and say, please give me exactly 1 times column vector number 3, it will give you exactly formula 2. Now, we also know how matrix multiplication is made, and there are some quick comments about it. And this means that it's just applying the matrix B multiplied from the left on the matrix A by applying it individually on the column vectors. So if you recall how you're doing matrix multiplication, that's exactly what you do. It's also the only way to have a reasonable multiplication of these rectangular schemes, which is compatible with the linear mapping composition. So we just want to say we store the information about the linear mapping. We don't know how to store all the values of a linear mapping. We just store the values of the unit matrix, unit vectors. If we know that, we can rebuild everything by doing linear combination using the linearity. Now, if we compose 2 linear operators, we get a new linear mapping, and that also has a matrix representation. And the only way to do it, so it's deductive from the abstract point of view, is the standard matrix multiplication. Now, of course, you cannot combine a mapping from R3 to R5 with another mapping from R7 to R12. It has to fit, so the target of the first mapping, which is applying the matrix A in this case, we are doing left matrix multiplication as usual, has to be the same as the domain of the second operator, which is matrix multiplication by B, and I simply call it the domino principle. So recall this slightly psychological disturbing phenomenon. If you describe the matrix as we do it in terms of m times n, height times width, it's going formally in the opposite direction. It goes from Rn to Rm, North Pole to Marta. And so if you combine 2 matrices, of course, the target space is the target space of what has been applied at the end. In my case, I write it CK, I think. And the domain is Rn as usual. So what is all this saying? We have linear combinations. And if we do linear combinations of a set of unit vectors, or more generally of basis vectors or vectors in some vector space, we can recalculate. We can say, well, which vector has used how many times? And the right machine to do it is matrix multiplication. So this is one of the key principles of linear algebra. And the most important special case is, of course, which you all know, is the case that you have square matrices. So m equals n. In this case, you're starting with n vectors, and you take linear combinations. And then it turns out that you're getting a mapping from Rn to Rn, and for such mappings, domain and target are equal. It's meaningful to ask whether it's invertible or not. So take a look at the definition of invertibility in the first formula here. It says that you have, and I will use 3 by 3 for the illustration, another 3 by 3 matrix B, which multiplied to the left and to the right gives you the identity matrix. So you have further down the identity matrix, which is I of 3 in this case, in MATLAB. Okay, but it's an important fact coming from the considerations in linear algebra, which I do not recall in detail, but I would like to remind you about why it's valid. It's actually good enough to know that you have a left inverse or a right inverse, and that's already the inverse for the matrix. I would like to tell you, please look up in a good linear algebra book, for example, the book by Gilbert Strang, and he will tell you that the Gauss elimination is the workhorse of linear algebra. So you all know how to solve a square linear system by doing Gauss elimination. Now, Gauss elimination actually means we build the inverse matrix by elementary operators. We add multiples of columns, rows to the matrix. We rescale and reshuffle the rows in the matrix. But at the end, it means we're just doing a left inverse, and magically we also have the inverse. While it's not completely magic, the basic fact behind it is a geometric fact. So assume, for example, that B combined with A is the identity. Because you're applying B at the end, the range of B must be the same as the range of the identity operator. So it means the columns of that square matrix must be everything. Sorry, that's true, but it's not helpful. But the argument should be the matrix A has to have columns which are linear independent. Because assume they were linear dependent, so they would kind of glue together, they would have a linear relationship, then applying B, that linear dependence would also stay. And then the range of this mapping B with A would be less than n-dimensional. There is some linear relationship of n vectors in an n-dimensional space, and that would mean that you can only get the identity if A is injective. But A injective means the columns are linear independent, and then you use the geometric argument n linear vectors in Rn are giving you a basis. The opposite argument would be if you are having A now to the left, then the range of A, the columns of A must span the same space as the identity operator. So the right identity means the columns of A span Rn. But if somebody is giving you n linear vectors which span Rn, they have to be a basis because they cannot be linear dependent. If they were linear dependent, you would have one linear relationship, and the range of the column space would be at most n-1 dimensional. Okay, so summarizing, we have matrix multiplication. It's made such that the matrix multiplication corresponds exactly to the composition of linear mappings corresponding to these matrices. I may add some extra box when I work out the details of this slide, these notes. And I would like to say, well, we have the following situation. Going back to the first relationship, the columns of A are a way to store the information about the linear mapping in an efficient way. Because of the linearity, knowing the matrix at the unit vectors is all you need to know the matrix. Now we have composition of linear operators, and linearity is, of course, preserved. So doing it twice, 3 times, whatever, it's associative. You will have, again, linear mapping. So there must be some way of putting the information from the first linear mapping A and the second B into a new scheme, which you call C. And we have learned how to do it, but it's a thing that is built in MATLAB. And what I will try to do with linear systems and translation linear inverse system, I will tell you, we can store the information about such a system by the impulse response or by some particular linear functional. And knowing this, we need a way to combine 2 linear mappings or 2 systems, and that will bring us to convolution. So convolution is not a magic thing. It's not like in the course of Brad Osgood, which I like very much. I recommend the YouTube talks of Brad Osgood in Stanford and about Fourier transforms. But he says, well, let's see what happens if we multiply 2 Fourier transforms. And he does a reverse engineering and derives the convolution relation from this. But I think convolution is coming first. It's just a natural way of encoding the information in the translation invariant system through the impulse response in the engineering terminology. And I will try to make this more lucid for you, explain it from the mathematical point of view. Okay, I think I don't have to talk more about matrix analysis. So probably you know all this. It was maybe only a different angle. And I will hopefully be able to start GeoGebra in a moment, but first let me come to the prototypical space, I would say, for a coordinate-free vector space, in this case, a four-dimensional space. And I just choose 4 dimensions to tell you it's something that you cannot imagine the vectors as column vectors because people have difficulties with components in R4. But you can plot them, and cubic polynomials look better than quadratic polynomials only. So let's look at the space of cubic polynomials. And we all know, and for exercise, I think you can try to repeat with your own ideas and with MATLAB and GeoGebra the same thing for quadratic polynomials where things are a little bit easier. So in the middle of the slide, you see the basic description. Cubic polynomials are, of course, in the space of all functions on the real line, or if you want, in the space of all continuous functions, or in the space of all differentiable functions if you want, but let's say in the space of all continuous functions on the real line, you take 4 functions and you make all the possible linear combinations of this. So you see here, the standard way for mathematicians would be we start with constant 1, which actually should be x to the power 0, not x sub 0, sorry, I will correct this. And then you take x to the power 1, x to the power 2, x third. So you take the monomial basis in increasing order. This is how the monomials would be described in mathematics. Now, we have already seen in our MATLAB experiment that MATLAB is having the opposite convention, which also has some advantages. So I'm calling this the M_3, which is you take the exponents in decreasing order. So we start with the leading coefficients. So if I want to view the polynomial x squared plus 2x plus 3 as a cubic polynomial, it has to have 4 components, and it will be 0, 1, 2, 3. If you evaluate it at a 10, you have 123. And we all know how convenient it is to look at these integer numbers to see by the lengths immediately which one is the bigger one, how to read it. Kids learn to read this as 123 and so on. So it has some advantages. The lengths give you maybe the actual degree of this polynomial in the strict sense, but we are taking all linear combinations. For illustrations, we use usually polynomials with leading term non-zero, means x third power, but that's all. Now, it's clear that these polynomials are a vector space. It's also clear that the representation is unique, and there are many other properties of these polynomials. For example, a polynomial of degree 3 has exactly 3 zeros. So this is very good because you can write it in the standard way as a product of the 3 zeros. That's actually how I will build the cubic polynomials that I will use for illustration. Going on, I would like to mention, because switching to GeoGebra and so on is a little bit cumbersome still, I would like to first go through these slides and then go to GeoGebra and then come to the actual material of the course. But I think it's important to give you an idea that whereas it's true that by mapping a polynomial, which you may think of a curve, to a sequence of coefficients, or by giving a sequence of coefficients and plotting it, you can have an equivalent description. It's not just an equivalent in the naive sense, but in the sense of vector analysis. So it's an isomorphism. You can add coefficients and you will get the sum of these polynomials. GeoGebra is very nice. You will see it that you can write the sum of 2 polynomials, the product of 2 polynomials in exactly a mathematical way, and you get what you should get. Now, in the abstract viewpoint, it will be very important to talk about linear functionals, or the so-called dual space. And as I repeatedly mentioned, going from column to row vectors is very naive and not telling you what you should have in mind. However, if you take the cubic polynomials and you use now the prime, later on sometimes people use a star, so I'm talking about P3R cubic polynomials and all the linear functionals. So these is the dual space of the linear functionals, and that space is the set of all linear, think of it as linear measurements. So now the next line is a kind of a mixture of an engineering terminology where I still write P of x. Soon I will leave out the x. So I'm saying a linear functional sigma is a mapping which assigns to each polynomial some number in the real or complex domain, depending on what we are using, so that in the basic idea, any linear combination of two or more such polynomials will give you a number which is the same linear combination of the values. So usually people split this equation into two pieces. They would argue that you have alpha equals beta equal 1. So you're saying it's compatible with summation. So the value of sigma at the sum of two polynomials is the sum of the values. Or they would just say alpha equals some number, beta equals 0. If you rescale a polynomial or a vector by multiplying it with a number, the output will be correspondingly multiplied. But of course, by induction, you are saying if it's true for 2, you can get it for 3 and 4, so for any linear combination. So for me, practically speaking, a linear mapping, or a linear functional in our case, is exactly something which respects linear combinations. Of course, you have to keep the assignment. Alpha is the coefficient, the first coefficient assigned to the first polynomial, beta is the second coefficient, and you have the same assignment here, but that's kind of obvious. Now, I want to kind of impress you by the huge number of possible linear functionals, also preparing for those that we need for signal processing. And I use already the Dirac delta notation for the simple point evaluation. So you're giving me a polynomial, we agree to evaluate it at a point x0, that's now a correct x0, and then you have a linear mapping. Why is this linear? Well, how do we define the sum of two polynomials? Exactly by adding the values. So it's by definition more or less a linear mapping. And later on we will also talk about continuity and what it means to change a polynomial to another polynomial. Of course, we will talk about changing the coefficients a little bit, and you will get similar coefficients if you know where you evaluate it and so on. But this is not relevant for now. But we also know that a polynomial can be derived. So if you first take a polynomial, you choose a point, I should have said y should be a fixed point, and then you take the polynomial at the derivative at a fixed value, so this has to be thought as a fixed value. We will use this notation and call it not delta, but delta prime. So in the theory of generalized functions, there will be an operation which allows to do such things, but for now it's just a symbolic. So it is definitely linear because it's a composition of deriving things which is linear. We all know that you derive a polynomial by doing it term by term, and constant factors are just pulled out. That's exactly linearity of the differentiation operator. And so this is another way of doing it. Of course, you can repeat it. You can take a second derivative and a third derivative and all these things. Now, integration is another procedure. And actually, if you look at many books, especially books in physics and also to some extent engineering, whenever they are using linear operations which have to do with functionals, they would prefer to write it in such a way as integrals, because people are used to use the linearity of integrals. as a mathematician and also from the point of view of generalized functions, it's much better to say, well, this is a special case, and don't use the analogy of this, the good properties of an integral to also for non-existing integrals, and the Dirac delta integral is a good example. But rather say, well, we're talking about linearity in many procedures, and it's true that any linearity discussion with functionals includes these special integrals. Now you can put weights, so instead of doing this, you're putting a weight function. So for example, if you produce, I mean, you're saying I have a map, a street map, and I would need some energy to bring my car over those 10 kilometers. Now, depending on the how to say, the steepness of the road, think you are going up a mountain. Maybe in the flat area case, a small value, you need very little energy to get for the first 5 kilometers. Then for 2 kilometers, it's fairly steep, so you would put k very large. Then it's a little bit more flat, and you would put k a little bit less. So if you think of k as a multiplicative factor, which tells you how much more energy per distance you have to do, then the total energy, you do a Riemann kind of approximation. You say, well, first I think it's constant over 1 kilometer, but then you say, but it varies over that kilometer, then you do it with meters, centimeters or so. If you take the limit, that's exactly the integral, so that the total energy maybe that you need for your electric car to get up the mountain, knowing the energy consumption with a weight factor depending on the steepness of the road. So it's not an artificial object, but something very natural appearing in physics and in many applications. Now, this is already a more general integral, and maybe 100 years ago, people were saying, what is the most general integral? I just mentioned it for, I would say, general mathematical education here. It's not so relevant now. And they came up with the Riemann-Stieltjes integral. So they would say, instead of having k of x dx, they write df of x. And they say, well, more or less, as I mentioned in the example, f is the height difference. So if you are in the area for an interval where p of x is almost constant, and you know that f is growing very steeply, then you would take the f at the end point minus f at the original point. Now, of course, if f is constant, if f is just, the identity operator, so it's equal x, you would get a Riemannian sum with x5 minus x4, x7 minus x6, and you would take any value p of the integrand in this interval, and you would show that this has a limit and that the Riemann integral. The Riemann-Stieltjes integral is the same thing with a variable weight on the length of the interval or the force needed locally. And the most general case that you can do is a function of bounded variation, which is simply a difference of two monotonic functions. So a function on the real line, if you extend it to infinity, would be a function where the total amount of going up and down is finite. And it's actually what you're facing when you're kind of doing a bike tour with your app. A modern app would say, well, you went up totally 500 meters because you went up 200 meters, then you went down 50 meters, then you were again going up and down. And so more or less you split the f into the parts where it's going up and going down. And then you get a general function of total variation, finite total variation. Later on, people were doing the same thing for two-dimensional, multidimensional things. And that's how measure theory came up. From measure theory, it's an integral part leading to Lebesgue integration. All this will not be needed in the current course, but I would like to give you at least a glimpse of how this is related to more mathematical things. Okay, we are now in the situation of having a huge number of linear functionals. And I would like to keep it at this moment. Yeah, okay, one more thing is that these linear functionals, I'm talking about the dual space. Now, dual space refers to the fact that this is again a vector space. So if you take sigma 1 and sigma 2, you can easily check that the sum, or 3 times sigma 1 plus 5 times sigma 2, any linear combination of these things is again a linear functionals. So you get a huge collection of elementary building blocks that you can build and more things. And at a different level, you can say, well, but isn't P3, the cubic polynomials, isomorphic to R4? So you just have 4 coordinates, so shouldn't it be just a 4-dimensional space? We also know, and it's kind of confirming this a little bit, that if you're given 4 values of a polynomial, then you can reconstruct the polynomial. If you're given 3 values, you can reconstruct the polynomial already from those 3 values. We're talking about cubic polynomials here. So somehow it's plausible that this dual space will be also 4-dimensional, but in order not to distract you, I would like to leave it here for the moment. So we have now a nice space, and we have the functions, which you can think of the signal space, and we have the functionals, which, especially if you think of the first one and maybe number 4, can be taken as measurements. The first one is a precise point value evaluation. If you think of K being very well concentrated near some point and total mass 1, so integral K of x dx equal 1, then you would say, I'm having a sloppy measurement. Maybe it's a rectangular function over some small interval with area 1, so a compressed box function. Then you would say it's a mean value. So I don't know, maybe you have a moving object and you have stopped how long it takes to move between 2 light bars at a distance of 1 meter, and you know the time, and then you're saying, well, the speed at the moment of passing, which is of course an average speed over, I don't know, maybe 100 milliseconds, is this and this. So kind of think of number 4 as a realistic way of measurement, and 1 is the idealistic measurements. But all these functionals can be thought as elements of a space. And of course you can say, well, in reality, maybe if you think of image analysis, we have a scene and a group of people is taking pictures with different cameras, with different resolutions or so, and they all get these measurements. And then you would say, well, they're all approximations. So somehow the high resolution image is a better approximation to the perfect image, but because our eyes or our ears, all our senses are imperfect, fortunately we don't observe a difference between a high resolution pixel image or high definition television screen and the values that we would have in a continuous analog world or so. Yeah, here we have the comment. The space, the dual space, is a space of itself, which allows linear combinations, and you should think of the linear measurements. So it's more or less the pairing of your signal space model, which on purpose is a simple one here. Cubic polynomials are not modeling a good real world situation. Already better, maybe I should mention that cubic splines, so gluing together cubic polynomials in such a way, gives a good model for continuous curves in general, so they are used in computer graphics. But let's stay with this idea. You have the signal space and you have the measurements, and the numbers that we get actually should depend in a good way, in a bilinear way. Linear in respect to the signal, but also linear with respect to measurements on the input. So it's pairing of functionals with elements of the underlying signal space. So mathematicians would say you have a space, a Banach vector space, later it will be a Banach space, and you have a dual space, which you can also endow with some norm, but this is coming with the concrete examples. Let me just mention the different representations of a polynomial. So mathematicians would use the first formula with coefficients alpha 0 to alpha 3. And here the advantage is that the label is corresponding to the exponent attached to it. This is convenient but not compatible with the idea of MATLAB. Well, you describe a cubic polynomial also in MATLAB with 4 coefficients, but in this way that you are getting a vector of length 4. And it doesn't have a zeros and the third component, it has the first and the last component. And because we have 4 vectors, you would write A1 to A4. So that would be polyval of A at X. That is, that would be the evaluation in the sense of a vector. In MATLAB, actually, we have to think of the same thing in opposite order. So you would actually polyval, here it is, vector B with 4 coordinates starting with the first to the last coordinate. And of course, the B is the flipped version of the A, and the A is a relabeled version of the alpha that mathematicians would use. So please keep this in mind. We will use this over and over again. And actually, later on, just going ahead, I will try to tell you that the FFT, or the discrete Fourier transform, is nothing else but given a vector in any format and going to the values of the corresponding polynomial as a polynomial on the complex domain evaluated at the unit roots of order n. But in this understanding, you have to understand that polynomials can be described in different ways, and unfortunately, or traditionally, even in the Fourier theory, when you try to illustrate it with MATLAB, of course, you are following the MATLAB conventions for polynomials, but MATLAB itself following the traditional interpretation, which is more like the first formula for the discrete Fourier transform. So that will be an easy game once you have digested it once, but it's creating a lot of confusion if you read engineering books and so on. Now, I would like to continue with the observation that we have also operators on this space. And you see here the operators are not matrices. At least I'm trying, maybe I'm showing not the matrices right at the beginning, but we are seeing that you're just manipulating the functions. So if you have a polynomial, you can shift it. And we have seen if you take a plus 5, you shift to the right if you take the argument 5 positions to the left. We can do dilations, we can do a derivative, we can combine it, we can do higher order derivatives and so on. Maybe it's nice to think of a matrix representation. So I was telling you every finite dimensional operator allows to describe linear mappings by a matrix of corresponding size. So what are the 4x4 matrices describing these operations? And I will show you only the first one explicitly. So we're talking about a shift operator, and to make it most simple, I was taking a equal 1. So a right shift by 1 unit on the real, or if you want also on the integers. How would you describe it if you work with polynomials? Now, such experiments usually I do with MATLAB, and so I would like to choose the monomial basis in decreasing order. So I would use cubic terms first, going down to order 0, and then the matrix looks like this. And the left shift has another matrix which looks like this. Now, if we were in classroom, I would ask you, does this remind you of something that you know, which you're familiar with? Here I have to say, well, probably most of you, after looking for this for a while, will say, oh, the columns look familiar to me. 1, 3, 3, 1, and 1, 2, 1, 1, 2, 1. Well, we have to think about the basis. So maybe we take the second column, and the second column is describing what the mapping, which is a left shift now, is doing to the second basis vector. So going back to the intuition that we are talking about the second monomial vector in the basis of MATLAB, which uses decreasing order, so x3, x2. So it's second power. Okay. So what is shift operator to -1? So replacing p of x by p of x minus -1. Oh, that's x plus 1. So what is x plus 1 squared? Well, this is a polynomial, clearly, and you have to describe it in terms of the basis vectors of cubic polynomials. So if you go down the second column, it says it's supposed to be 0 times x third power. Yes, there's no cubic term appearing by squaring x plus 1. And then you have x squared plus 2x plus 1. So you go down the columns, you get the coefficients, you get the description of this image of x of x squared under the mapping of the left shift, which means you're writing the coordinates of x plus 1 squared. If you go on, of course, maybe now the first column is also clear. If you take the third power, we all know it's x third power, 3x squared, 3x, and 1. And that's now where you get the minus in the first matrix here. If we have x minus 1 third power, so it's the image of x third under the right shift. The right shift needs a -1. So you have 3x third power minus 1 times x third power, leading term, minus 3x squared. We are in the second row, which are all the coefficients which correspond to the second element, which is x squared, plus 3x minus 1, and so on. Now, I don't think I have to switch to MATLAB in order to convince you that, of course, if you want to invert a linear mapping, you have to compute the inverse matrix. So a good way to do this is to say, well, just take one of these matrices and compute the inverse, and you will find maybe up to numerical precision. Maybe you take a round operator at the, but up to numerical precision, you will get exactly this. So it's not only that left shift is undoing a right shift and so on, or the composition of two matrices. Maybe I take the square here of this operator, which is left shift by 1. You would, of course, get left shift by 2 and 3 and 4. And you also see the binomial coefficients popping up here. So it's a nice thing. You can represent this operator. And then, and now I leave it a little bit up to you or for discussion, because it's not good if I give the answers right away. You should think, well, which one of these operators that you have here in this list are compatible with the translation operators? So of course, the way how you can verify it, that you can say, well, now I'm building the matrix corresponding to a dilation operator. Maybe I just explain how that would be rather simple. I mean, dilation is mapping x to the k to r times x to the k. So clearly you just have to write it's r to the power k in the row number k. So it's more or less a diagonal matrix, not more or less, it's a diagonal matrix with exponents r to the k. So it's r third power, second power, first power, and 1. In the diagonal, that's the dilation operator matrix. And then you can test by taking a random shift or so, whether an operator is commuting with shifts or not, and you will have some observations. Now, what I would like to do and what I would like to explain to you in the next part is to use GeoGebra and to convince you that you can understand without any matrix theory, just playing around what you could even explain to high school students, that, for example, one translation is commuting with another translation, because we all know shifting by 3 and then by 5 is the same as shifting by 5 and then by 3, so it's shifting by 8, of course. And taking derivatives probably is also commuting with translation. So, well, there are some linear operators on the space of cubic polynomials which commute with translation. And we will try to explain, and I'll leave this more or less to the Thursday meeting, how to do it, how to code these operators and connect the invariant systems with linear functionals. And again, my reasoning for doing this, and that's kind of the first time I'm doing it in a course in such a detailed way, is to say polynomials are familiar to everybody. We know all these operators. It's nice to recall linear algebra concepts by doing the matrices, and so overall we will learn a lot from these matrices. I think it's a good moment to stop here. I will switch screens to GeoGebra and suggest to continue in circa, I would say in 5 minutes, 3 to 5 minutes. No, I will be back in 3 minutes. We start at 9:08 then with the second part. Okay. I am resuming now the course, and I would like to show you how we can use GeoGebra in order to obtain illustration of the polynomials, and also to prepare for the mindset which we will use for the description of translation invariant linear systems. So you learn hopefully various things which you know in principle, but maybe not from this angle. So I have already started to prepare 2 points. I would like to produce a standard cubic polynomials with zeros at the most simple points, meaning at -1, 0, and 1. So I put the labels x0, x1, x2, and I put this 0, -1. And the good thing is that I can make these things visible on the GeoGebra screen, and then I can change these points later on. Now, we all know that the polynomials are products of linear factors, and clearly the linear factors are of the form x minus x0, and you see immediately you have it, this line represented. So we have g1 of x is just x minus x1, and we have g2 of x is x minus x2. So it's a perfect collection of lines or so. Now, the nice thing is that we can say p of x, or I will try to do it directly. P is just g0 times g1 times g2. Yeah, that's actually very nice, because what you can see here is a kind of the use of mathematical terminology. So my input was just P equals G0 free space, meaning multiplying, times G1 multiplied with G2. But GeoGebra understands this as a pointwise product with brackets. X minus 0 is, of course, x. And you see that it will have exactly the right zeros. That's clear. It will have a positive part here. That's clear, because minus with minus is minus, or positive with positive is positive. So it will be positive above from +1, and it will be positive between 0 and 1, and will be correspondingly negative on the other ones. It also shows you that such a function, you can expand it, of course. It's a cubic polynomial, is something like this. Now, what I would also try to show you is that the shift operator is done very easily. So maybe I should, don't use this, but I should call it A for convenience. I do a shift parameter, which we also can move around later on, and we say PA is the TAP is just P of x minus A. So you're just taking a shift, and well, not much has changed, just the color has changed. Originally P was like reddish, and now it's a little bit violet or so. But that's of course because if we do a shift by 0, it's no movement or so. But now I'm doing a shift, and you see if I move it A equals 2, is the curve has exactly zeros now at 1, 2, 3. If I shift it to -3, the corresponding zeros will be moved to -4, -3, -2, and so on. So we can do very easily visualize the effect of these things. Now, I'm trying to show you kind of experimental evidence without any matrix theory and without any rules, so to say even, that GeoGebra allows you to verify that the derivative is a translation invariant operator. So it's plausible from the geometric point of view, of course. You are looking at the picture and you're saying, well, if you ask me where is the turning point, where is the tangent horizontal, then of course if you move the function from the orange graph to the violet graph, it will move correspondingly by -3. So whether I first determine the tangent to a curve and then move the curve, or first I move the curve and then determine by the rules of differentiation to this place, it must be the same, but we can do it also here. We can say derivative of p of x is just p prime of x in naive way. And you see, of course, the gray curve that you have here is a negative curve. It has a turning point, of course, exactly at 0, as we expected or so. And then we can say TA of derp is just derp at x minus a. Okay, so this is visually already convincing with the fact that you have the gray curve. It looks like it is the new brown curve is just moving the gray curve to the thing. But what we should do is, of course, to say no. We expect that this is the same as the derivative of the shifted version of the polynomial. So it should be top prime of x. And maybe you have observed that this was brown and now it turned into green. So for example, if I take away the brown color, you just have a dark greenish thing. If I take away, put it back, and if I activate only the brown one, it's at the same position. Now, I find very important for understanding of these things that now with all these, in this way of building up the GeoGebra, you can do everything in a dynamic way. So what if we are shifting not by 3, but by 4 to the left? Then, of course, the whole situation is changing. Maybe we don't have to look at, if you don't want to see this originally generating line, just concentrate on the curve and the derivative. So the parabolic shape is the derivative. And now we are doing an animation. So we let this move around, and you see it's shifting by negative values, 0 now, then by positive values or so. And so in this way, you can get very good things, good impression. So of course, derivative is a non-trivial translation invariant system. It maps the cubic polynomials and stop the animation. It puts polynomials into polynomials. Now, if you want to see the effect of changing the zeros, you just have to move the points, let's say the second 0 to the left, then maybe you move the other one, the middle one, a little bit more to the right shift or so. But of course, if you shift everything, the same is true, of course. So if you see such pictures, of course, it's good to go to the algebra and verify that differentiation is satisfying this. But personally, I think that such a thing is really more convincing than just doing algebra and computing things. Actually, like a small comment when I saw the book of Martin Vetterli, which is a great book, which is free available or so. One of my ideas was, okay, these poor engineers, they have to do so many computations to get to their results, whereas they always claim that they are working based on intuition. But I think there is more and more a gap between intuition being replaced by experience, meaning experience with juggling with the symbols and things which you are allowed to do and things which are not allowed to do. On the other hand, I mean, now I'm doing a more formal general comment. People in mathematics are too much interested or concentrating on correctness. So it's like they are overcorrect and they don't recall anymore why we are doing certain things. And so it's especially one of the goals of this course for me, that I would like to narrow this gap to help you to understand, if you're more applied, how to understand what mathematicians are doing and how you can do it in a correct way. Okay. I just hear that somebody couldn't see the animation, but I hope this problem is solved meanwhile. I will stop the GeoGebra anyway. So, okay, so I'm coming back to what I would call also orientation comment or so. That means I'm not doing a mathematical course in a strict way. I'm not doing a really applied course, but I will try to bridge the gap between the two fields. So if we would talk about touristic activities or so, a pure mathematician would be exactly a guide who is doing a tour which you can book, and it will be a 3-hour tour. It will be a fixed tour where it's clear what you get correct information, or you get as much information as you can get within 2 hours or so, but there's no deviation from the original place or so. Or if you would think of music, it would be a classical musician. I mean, he cannot change the score just because of fun. I feel more like a person saying, well, you would like to explore the town, and I tell you, well, let's get on the bus. Sometimes we get a bit of overview. Then we get a bit of orientation by reading some maps. Then I tell you some story. But overall, at the end, you have a much better overview over the situation. So in the musical situation, I would be more like a person playing a jazz standard, where of course the basic melody is clear, but the variation that is chosen for at a given moment may be completely different from doing the same thing again the next day or so. So this recording is just one example of how one can try to explain this. I will stop now the GeoGebra and go to the script, and because I think the mixture between illustration and kind of serious formal presentation is allowing you to refresh and restart and get back to track. So I hope to change now to the screen with sorry, may take a little moment here. So not here. Sorry, it takes a little bit. Because the screen doesn't show my slides. Still has the old one. Maybe I... Okay, so now let's come back to the script and to the kind of models for the signals that we actually want to use. So I think it's reasonable to say, when you think of a recording, that we have a continuous function, and whereas the polynomials are cubic polynomials are unbounded functions, which are not even uniformly continuous, I will stay with the bounded continuous functions, and especially I will try to concentrate on the concept of Bibos systems, so linear mappings or channels or systems which map bounded functions into bounded functions. If you think in a realistic way, I think it's not really a restriction to look at bounded linear mappings from CB into CB. So I use the symbol C sub B for bounded continuous functions. And at some point I will explain maybe a little bit the problem that you have if you model functions, if you model operators using this space, because essentially it's too big. So you could have input which is lasting forever, not decaying, and you could say we watch it for all the times, and at the end we have some observation. So it's simply not true that you can represent bounded systems mapping CB into CB by linear functionals. That would be nice, but there's a little mathematical catch. That's one of the many reasons why I'm using C sub 0. So within the space, actually we are saying in practice you only have signals of finite duration and you observe them quite long. So I would say the Bibos system is a system where the input will be some test signal which maybe lasts for 3 hours, or I don't know, you have a vibrator for geophysical explorations, and it vibrates for 1 minute. It does a frequency sweep in order to analyze the response impulse for all the frequencies. But you are not thinking of something which lasts for hundreds of years or so. Of course, the time series is a different thing, where you have, I don't know, maybe 500 samples, but in audio you have 44,100 samples per second. So you are saying the piece begins at some point, it ends at some point, and you want to do the frequency analysis of a piece of music, and that's what is realistic. We have already discussed a little bit, and I don't go again into the details, that Tx of f is the shift operator, and those functions which are having this property that shifted versions deviate very little in the sense of the sup norm are the functions which are uniformly continuous. And that simply means that in the epsilon delta game, you don't have to know where the test will take place. If I claim a function is uniformly continuous, you can give me any epsilon without telling me where you will test it. I have to come up with a delta, and then you can go to the worst case, so to say, the steepest part of the f, and test whether my delta interval is small enough to guarantee the deviation between of f of x and f of x plus y near x by delta is small enough, measured in this case. So that's kind of, I don't go into details. I just want to mention in between, because we have it here, that for operators which map normed spaces into normed spaces, you have an operator norm, and it's just saying, well, how big can something be which is of norm 1 at the input side, at the output side? So if you're mapping from C0 or CB, so every space with sup norm, you are saying I'm determining the sup over all those functions where maximal value is 1, and you look at the size of this. So maybe a Bibos system would be whenever you have maximal value, absolute value 1, the output is at most 5. Of course, you know that if the maximal value is 10, it will be 5 times 10. So the linearity allows you to deduce a lot of further estimates from this simple estimate. And we also will see that the norm of a matrix that you can compute with MATLAB is just the operator norm in exactly this spirit, where you take the Euclidean norm for vectors on the input side and on the output side. So this is quite natural. Now there's a lot of abstract things which we skip for a moment, but I would like to do it by concrete arguments. So I'm claiming, and I'm going a bit slower, that CB is a Banach algebra with respect to pointwise multiplication. Well, you don't have to read the rest at the moment. It's just saying, well, we just do not have only a vector space structure. You can do linear combinations of bounded continuous functions, but you can also do a pointwise multiplication. Okay, and then the B star properties. You even have involutions, which means linear operations which you have applied twice, you're back to an identity. So for a function, you can take, if it's complex valued, you can take the conjugate, or you can take the flip operator, or you can take the combination of both of these operators. So there are different involutions in this. That's useful later on, but not important for the moment or here. Now, if somebody is giving you such an algebra, and we will discuss this separately further down, then you also have to ask, what if you have subspaces? Now, this statement number 2 is quite useful. The uniform bounded continuous functions are a closed subalgebra. And that means, with respect to the ordinary multiplication, the product of two uniformly continuous bounded functions is again uniformly continuous. And if I say it's a closed subalgebra, it means if you're giving me a limit of uniformly bounded continuous functions within the bounded continuous functions, then you will get again a uniformly continuous function. So you cannot get bad properties by something which can be approximated by those better or good guys. And C0 is a closed ideal even, and the closed ideal is even a closed subalgebra, so it's closed. Okay, that's good. If you take a limit of functions vanishing at infinity, it will also have this property. And the ideal property means that if you are multiplying, and we will do this in detail, if you're multiplying a function which is vanishing at infinity with a bounded continuous function, then you will get a function which is also vanishing at infinity. CUB does not have this property, as we will see in a moment. Okay, so maybe I skip this or have done this already, just reading the lemma. C0 is the closure of the function with compact support. Remember, CC means continuous complex valued functions, and sub C means with compact support. So these are the usual functions that you would plot. You would, by hand, you would make start somewhere, end somewhere. So continuous support means in some interval minus n, and everything is happening or so. And it's quite plausible if you have the last property. I mean, if somebody has functions with compact support, clearly they vanish at infinity. They are small because they are 0 near infinity. If you take limits of such functions, if this is a true statement, you will get also functions which are in C0. While on the other hand, if somebody says the function is very small and of minor importance at far out, so near infinity, well, you just take the important part and then you continue it somehow at the outer part. Or as I would suggest, you multiply it with a continuous plateau function. We will do this a lot later on. And you get a function with compact support, and you have to check it's close as much as you want, and that's different. Okay. So I think I have hopefully put that already into the slides. So some of these things will be discussed later on. Okay, now it's the question whether, sorry. Okay, I tried to visualize the subnorm in different ways. So remember that a function of the real line, you can think of a function of time, in the complex planes is like taking a pencil and putting the value, the f of t, at some point in the complex plane. So xy coordinates, Gaussian plane or so are quite clear. A continuous function is just drawing this, and here I have just taken a trigonometric polynomial, which is a continuous periodic function. And the least radius that you can take to encapsulate the whole graph of such a bounded function is this. Now, a function which is vanishing at infinity means at the end of this graph, you will concentrate near zero, and it's clear that this is a bounded function or so. Now, there are different ways of saying that the subnorm distance is small. So I was taking two functions, and those two functions are compared, and I'm saying, well, the subnorm or the distance between g and f is just epsilon. Now again, if you have two functions and they are complex valued, it's very not so easy to visualize the real the complex valued functions. And if you go to the absolute value, it might be that you have a function which has the same absolute value, but one has plus minus ones or is taking values in the unit circle, and maybe a pure frequency, any pure frequency is absolute value 1. So you cannot compare the absolute values. However, of course, you can compare the real parts separately, the imaginary parts. And if you know that real and imaginary part are close by epsilon, you find out that the complex parts are apart from epsilon times the square root of 2 and vice versa. There you're losing a little bit, but of course for visualization we have to take two real valued functions. So here we have the black function, and I'm saying f is a new curve, which is the red curve, and if it is between g minus epsilon and g plus epsilon, and this is, I'm taking epsilon something 0.2. I mean, I've scaled everything so that the maximum originally probably was 1. And so you can see to be epsilon close means you take an epsilon strip around g. On purpose, I didn't put the g itself because then the graph would be overloaded. But this is, of course, a symmetric relationship. So you could also do the same thing by starting with the what was a red curve and take it plus epsilon and minus epsilon, and then you would say, yes, this originally black curve, the more smooth object, is really in between this. So that's the same, the distance from f to g is the same as the distance from g to f. That's obvious because of the absolute value. But in terms of graphs, maybe you would argue that this second plot is telling you that this red smooth curve is a good approximation of this more juggling curve here. Or here you would say, well, the original curve was the black curve. This is the true signal that we would like to recover or so. But unfortunately, it was contaminated by noise, and therefore we have a red curve. But it's not very far away. So of course I made some relatively small epsilon to allow you to get some idea of what you're doing. So this idea is if you have a good approximation, you're within an epsilon strip if you think of the real and imaginary part. And of course, convergence in the subnorm means that these strips are getting more and more narrow. You get better and better approximations. For example, we'll see if you take a Fourier series of a function, taking more and more terms will allow you to have approximation, but it's not always true that this approximation is true in the subnorm sense. We will see that this is the famous Gibbs phenomenon. If you recover a rectangular, a box function from its Fourier coefficients, you will have some overshoot. So it will not be within the epsilon strip, but the overshoot occurs only in very small areas near the jump points of this box function, and that's why you have this. Now, again, some harmless remark. When I talk about an abstract algebra, means simply it's a vector space with some multiplication. And if I use a bullet, then of course, whenever you are having such combination of a multiplicative structure and additive structure, very often you require, and actually you have, such a rule which would be called distributive law. So you expect an associativity distribution law. We don't have to discuss this in a formal way, but clearly it means you multiply output put the constant in front and so on. So now let's come to these continuous functions. I have added now to the script, somehow I've had the wrong version of the file before, the fact that a normed space, so we have seen subnorm is a fine thing. If you have an algebra, and of course it's just pointwise multiplication, then you would like to have compatibility. So if you have complex numbers, you can multiply complex numbers, and you all know the size of a product of two complex numbers, absolute value of Z1 times Z2 is the product of two functions. Now when we come to more general algebras, that is the multiplicativity, so to say, is a very strong condition, far too strong for practical applications, but submultiplicativity. So the product shouldn't be larger than the product of the norms. Now, if you want to see a two-line verification with all the details, just look at what we have here. It's trivial and more or less the definition of the subnorm that all the values are by absolute value inside this. That's the smallest constant that you can put for such universal for all the values. Same for x. Now, what is the product function? It's the function which has h of x times f of x. Here I'm using the properties of complex numbers. Now, the absolute value of the product is at most, I mean, inequalities can be multiplied if everything is positive, is giving the product here. So it means that this constant here is a good estimate universal for all the arguments. Therefore, the minimal or the infimum formally of all these constants, which is exactly the norm of h times f, is giving you an estimate. So we are having a proof of 15. Or 15 is equivalent more or less to the validity of 17, universal estimate of this form. Now I've tried to illustrate this again, just a very harmless thing, because in the estimate above we estimate only absolute values, kind of I'm concentrated on this here. I'm saying, well, we have two functions, you don't have to look at too many details. We can either do the absolute values and multiply the absolute values, which gives you the black curve, or you can take the original functions, which are positive or negative. I'm showing only the absolute value, but then the blue curve is the absolute value of the product. So, sorry, no, sorry. Yeah. Okay, this curve is worked with the sum, but you could do the same with the product. So y is the norm satisfying the triangle inequality. That's the same argument here. So just put a plus instead of a multiplication. And so the illustration is unfortunately for addition. So again, the black curve is the sum of the absolute values. The blue curve is the absolute value of the sum. Now it's clear if you think for a moment, well, when are they the same? Well, you see occurrences where you don't see anything blue. I don't know where it is, but in some places the blue disappears under the black, and it's where both functions have the same value, the same sign. So the absolute value of two positive things is of course the same as the sum of the absolute values. And maybe I was also doing here, I should have just corrected the text and put the times here, because in order not to confuse you too much, I wrote down the details, the equality of norms. So when you can ask the question, when do you have equality here? And the equality occurs essentially if the maximum is taken at the same place. So it may happen that you have some particular value x0, where f and h take a maximal value. Recall, I mean, if you take a plateau function, f may take the maximum at many points. If one of them is also a maximal value of h, then you will have equality here. Otherwise, you're having an effect, which I tried to illustrate here. Read carefully the text, and I will probably also correct that later on. Now, question about multiplication. This is also a little bit kind of typical for what the kind of arguments that I'm using also during the rest of the course. Again, coming back to this claim that UB is a Banach algebra and the pointwise multiplication, so it's a subalgebra, and C0 is a closed ideal, which exactly means this. That's in terms of spaces. I multiply all these elements with all these elements I'm staying inside, and of course it means if you take any h in, oh, that should be, I have to correct this, should be in CB, f in C0, then the product is again in space. So this h in the last line should be CB. Okay, what are the ingredients? And you will see, not now. Here we are really doing the basic things where you do detailed analysis in a maybe cumbersome way. But once you have established those formulas, you can reuse them many, many times. And what we are doing here as analytic argument doesn't have to repeat it all the time. So one simple fact is, of course, if you shift the product, that's formula 1 in the proof. If you shift the product function f1 with f2 by the amount x, you can of course do the same by multiplying first, by shifting first f1, separately you shift f2, and then you do a multiplication. Okay, so if somebody wants to know, is the product functions given two uniformly bounded continuous functions f1 and f2 also uniformly continuous? And I will use my test. Go down 3 more lines. I have to observe whether I can estimate the shifted version tx of f1 times f2. And to avoid problems, I've made a bracket here, minus the original product or so. And in order to have an estimate, I apply the triangle inequality and some formal identities. So how can I estimate the two shifted functions, how can I estimate the difference between the shifted product and the original product? And the rule is never move things twice. So if you would climb a ladder, for example, you would not jump with both feet and try to get one step higher. You would first take the left and then the right, and that's exactly what we do here. So we insert an intermediate term. You are free to choose either txf1, I mean shifting only the first one, leaving the second invariant and multiply with f2, or try to do it with a piece of paper and a pencil to do it yourself with the other term, which is leave f1 invariant and insert tx of f2. So the identity is by inserting a term, so instead of 2 terms, we are in the middle of the proof. We have, and using distribution law, the shifted version of f1 minus f1 multiplied with f2. So we have the mixed term extra, and it reappears here with a different sign here if you look at the rest. And so it's a sum of 2 such things. Now, we have seen that the triangle inequality allows you to split the subnorm into 2 pieces. And the next step is where it says submultiplicativity. You can pull out one factor in this distributive term, and you get this. Now, in this part, maybe I should mention, actually, I should not have written tx, I should not have written the subnorm of f1. I should have written the subnorm of t of x f1. But you know, it's clear, if you shift a function, it doesn't change the subnorm. Or in other words, if you think of these red images, if you think of a complex valued function as a curve, changing the time parameter does not change the curve itself. It's just the points in the plane which are left over after the graph has been drawn. So it's clear that shifting an operator, maybe I should also put this at the beginning as an initial observation, translation is isometric. So that's why in this submultiplicativity estimate, the f1 norm pops up. And now the question is, okay, how can I manage to make this smaller than epsilon? And there are two traditions in terms of teaching such things. One is to say, well, I just assume that this difference between functions f1, f2, and they are smaller than epsilon, and I get something like 5 epsilon at the end and say, but the epsilon was arbitrary. I would like to say, no, you have been asking me to have an epsilon at the end. So I'm smart and introduce a new size, which is a positive number, which is the epsilon divided by the sum of the two norms. Because if I assume now, going further in the proof, that both for f1 and f2, I find there is some delta by assumption, such that I can guarantee that shifted versions are at most epsilon prime away from their original one, then I can insert this into the equation above, where it says submultiplicativity, and I get, of course, that you have epsilon prime for the difference terms, and you have the size of the functions f1 and f2, and you multiply out, and by setting epsilon prime suitably, you get epsilon. Okay, so we have managed that if you would give me an epsilon and two uniformly continuous bounded functions, I know how to find a delta, I know it exists, I can demonstrate it to you, that also the product has the same property now with the original epsilon, and everything is fine. The other thing is, and now I think it's correctly described, and I'm going now to this part here, if you multiply a bounded function with a continuous function vanishing at infinity, the h guy is in the big space, and the f very often will be a symbol from C0. Then, of course, we know h of x has some uniform bound. And now we are looking, and that's the last line of the proof, at the product function of x. And, well, it's a product of absolute value of h of x with f of x. H of x, independent where you are, it's controlled by the size of h, so it's some fixed constant. And this can be made small. Well, how? By taking the argument far away from the origin or close enough to identity, or practically by assuming that the radius is big enough. So for epsilon, and I choose, of course, epsilon prime to be epsilon that you have given me, here it is, divided by the subnorm of the h. And then you can say, I go so far with my small function, f, such that at the places we are less than epsilon prime, and because of this choice of epsilon prime, the estimate is ending with epsilon. So we have this concluded estimation, which again, going back to the theorem, or to the lemma now, means we have this inclusion, bounded functions multiplied with continuous functions is giving you something, vanishing at infinity is giving you something vanishing at infinity also. We will use this quite a lot, and maybe I mention also a basic property about now operators. So we have seen cubic polynomials are a nice vector space, and we have some very natural operators on the space of cubic polynomials, and actually we will see even derivative is bounded on the cubic polynomials, but of course not bounded on all the polynomials. Actually, we would have to choose some strange norm, but if you are just taking, in preparation of Bibo's system, the subnorm for the space, and therefore the operator norm, the magnification factor, I use this triple bar to use the subnorm over all the size of the output. So recall, this has been defined at the beginning of this part of the session. And then it's clear, a very simple property of the magnification interpretation, that the product norm of a function of two operators coming concatenated, so T1 is applied first, then T2, symbols appearing in the opposite order, but that's exactly like you have matrix multiplication, is at most the T1 with the T2. So it's again a typo because I was copying the symbol. I will correct this, of course. Okay, so the claim is even that, and now it's kind of a summary of the terms, all these operators are form a Banach algebra. and I just give you an outline, it's a norm. So it's a non-negative thing. It's compatible with addition of operators. It's also compatible with multiplication given by concatenation. And the rest is just a program. Then you have to show, and that's very nice and very important, but we do not do it now, that it's also complete. So we have to discuss a little bit the concept of Banach spaces, Cauchy sequences, and so on. And finally, we have to verify that this property, the submultiplicativity, is okay. But this is more or less, if somebody tells you, well, I have two operators. The first one has a magnification of at most 3. There's a shrinking operator. Everything is shrinking by at least a factor of 2. So the maximal stretching, so to say, magnification is a factor of 1/2. Well, if you compose them even in any order, the resulting maximal magnification will be 3/2. So that's exactly the product. So in this sense, it's absolutely not surprising. And again, it will very often be really a strict inequality. But if maybe one vector is magnified and then happens to be undergo the maximal magnification under the second also, then it may be equality here. And that's a kind of an interesting fact. I think that for now, time is over, and I thank you for your attention. I have seen that many of you have already looked up the recordings, and I encourage you to do so. And therefore, I'm stopping now the recording and